So we're going to finish up 2.5 tonight and then get into most of 2.6. We might finish up 2.6 next time, but I want to get the bulk of it done just because I want to finish 2.7 on Wednesday because your test is on Monday, and I want to make sure that on Wednesday we have time to talk about your test. I don't really want to say too much about it now. There's not too much to say, but we'll talk about it Wednesday. It will be something that I will be making available to you on D2L, so you're going to access it from there, but you're not going to be taking it like a D2L quiz like you did today. So it's going to be available to you, and then you'll be working on it and turning in your work. That being said, the turnout for the graphing homework was not good, and I think there are 10 submissions in there right now. A couple of you emailed me, and then I emailed you back and said, please upload this to D2L, and then you did. And then a couple of you may not have had time yet. So if you emailed me your homework before 6 o'clock and I asked you to put it on D2L and now you can't because technically it's late, don't worry. I'm going to open it back up for you. I'm going to go back through my email tonight right after class, and I'm going to make sure that I allow everybody access to get back in if you had already tried to send it to me, because I want to make sure that you're able to do that. I know it's new for everybody. Some of you had a hard time scanning your pages into one document. I know I suggested Genius Scan. It's going to keep scanning until you say you're done. So if you scan a page and then stop, move to another page and put your phone back over it, it's going to keep scanning until you hit the done button. So it's going to combine all those into one file for you. If you need help with that, stick around and talk to me after class, and I'll try to troubleshoot it with you. I know it's kind of hard to do that over the computer, but I'll try. And if I can get the lighting right, I can show you how mine works on the document camera. Let's see. If you have homework questions, stick around after class or come on Wednesday to the office hour. I just want to make sure we get through enough stuff tonight. We're running a little bit behind, so I want to make sure we get everything covered. And nobody was asking homework questions during the office hour, so it couldn't have been too bad. Was there anything in particular that was really bothering anyone before I move forward in 2.5? Okay. I will be putting up a review assignment. I'll probably put it up tonight, and it'll be review homework on my math lab. And it's going to be very similar to the type of thing that you're going to be doing on our test on Wednesday, which will cover 1.1. 1.1, if you don't remember it, was looking at the calculator graphing output window and talking about scale. So we did that in 1.1, and we talked about input and output values. 1.5, which was solving quadratic equations, and then 2.1 and 2.2 were all about functions, function notations, graphs, domain, range, increasing, decreasing, all that stuff. 2.5, we're going to finish up today, was about transformations of graphs. 2.6 is algebra of functions. Most of it is, I think, fun. And then 2.7 is a little bit shorter, but we're going to talk about inverses in 2.7, which is going to be really closely related to what we're doing in 2.6. So all of those sections, 1.1, 1.5, 2.1, 2.2, 2.5, 2.6. So it'll be 7 sections on your test on Monday. I will be putting up a review homework. It's going to cover all of those. But my goal is to just pick some relevant stuff, because I don't think it's very useful to give you a review homework if there are like 60 questions on it, because you're probably not going to do it if there are 60 questions on it. My goal is to try to just give you a little bit of sampling of what I think is most important in each section, and you can go through that on D2L. Of course, anything that I want you to graph by hand, if you see it on D2L, but you graphed it previously by hand, make sure you know how to do that. It will not be for credit. It's just going to be an optional thing. I might give out extra credit if you do it, but it's just going to be to help you sort of synthesize all your information so you feel like you're ready for the test. Okay, before I jump back into 2.5, any questions about this week or next week? Except for the nitty-gritty on your test, which we'll talk about Wednesday. Okay, let's see. Something's in the chat. Oh, it's just Gian saying that the quiz was fun. Awesome. All right. My 1-year-old has a really high fever. So in case my husband comes up here and it's just like, I don't know what to do. She's crying and won't stop. I just heard her crying a few minutes ago, and it's like tearing my heart out right now. If I end up having to cut this off early, I'll just record something and make sure I add it to the YouTube page. I think he should be fine and she should be fine. I hope so. No one else is sick. It's just her. So rough times for him tonight. Oh, well. All right. Then let's get into this 2-5. If you'll remember last time we left off, bring this back here. Share my document cam. All right, so we were talking about transformations of functions. We talked about how we can take a function and we can add or subtract a value from the function and how that's going to shift the graph up or down. Then we talked about how we can add or subtract a value inside the function and how that's going to shift the function left or right, and how the plus sign actually shifts it left, and the minus sign will actually shift it to the right. And then we just said that we could combine those two things. We could have something happening inside the function and then another something happening outside the function, and what would happen if that were to occur. Then we started talking about reflections. We can make an x-axis reflection by putting a negative sign in front of the function. If we want a y-axis reflection, the negative sign goes inside the function. Notice the difference. And then we worked a little bit with those reflections. What we left off on was talking about this concept of stretching and shrinking. And we concluded, albeit briefly, that if we were to multiply the function by some number, that it's either going to vertically stretch or shrink the graph. Now, I uploaded this to D2L. I don't know, probably a lot of you didn't think to look at it, which is fine. I had mentioned it, but maybe you kind of were like, okay, fine, I've had enough, and then you forgot about it. I get it. The big difference here was that when we took f of x and then we stretched it vertically, we knew it was a vertical stretch because the function was being multiplied by a number in front of the function, and the number that it was being multiplied by was greater than 1. The difference with g and h is that for h, the number that we were multiplying the function by was less than 1. So when you're multiplying the function by some fraction that's less than 1, you're actually going to end up getting this vertical shrink that's occurring. So if you can just kind of imagine taking this function f, and if you have a situation like g of x where you have a coefficient greater than 1, you're sort of just stretching the ends of it out. Whereas for something like h of x, you're taking this function f and you're sort of just compressing it back together again. And then you end up with something that looks like this purple function for h. So that was one of the last conclusions that we made. We said something similar occurs whenever we multiply inside the function. The big difference, however, is when we multiplied inside the function to get k of x, it looked much like the similar stretch that we got over here when we multiplied by 2, but it wasn't quite the same. It was actually a bigger stretch, and we ended up getting an even larger shrink when we multiplied inside the function. And that's because we're not actually talking about shrinking and stretching vertically. Everything is happening here horizontally when it's happening inside the function. So when you're multiplying the function by a value that's greater than 1 inside the function, it's going to be a horizontal shrink. That means that horizontally, your function's actually coming in closer to the y-axis, or wherever that central point is. Whereas with m of x, when you multiplied inside the function by a value that was some fraction of 1, you end up getting this situation where you're horizontally stretching out that function. And that's the big difference between these two examples. Was over here with our function, we were vertically stretching and shrinking, and then the one on the right, we're horizontally stretching and shrinking. And the opposite is going to occur when you're thinking about a stretch or a shrink. When it's vertical, the larger number is going to give you that more stretched out graph because it's being stretched out vertically. However, when you have a larger number in front of the x inside the function, you're shrinking it horizontally. So we made some conclusions here. So we said that g was a stretch vertically by 2, h was a shrink vertically by 1/4. And then for k of x, we had a horizontal shrink, and that's because the graph is actually becoming more narrow, and then a horizontal stretch for m because we were stretching that graph out horizontally. And then to make that general conclusion, a vertical stretch will occur when you're multiplying the function by some value c such that c is greater than 1, or a vertical shrink will occur if you're multiplying by some value c such that c is less than 1. And actually, I meant to specify that it was between 0 and 1. That's what I tried to include here, and then it ended up looking like an OK. This is supposed to be a value of c between 0 and 1. We can't just say c is less than 1 because we don't want to talk about what any negative value of c. It has to be some value of c such that the value is between 0 and 1. And then same idea here with the conclusion. When we're multiplying inside the function by this constant c, we're going to get a horizontal shrink if c is larger, like some number greater than 1, and a horizontal stretch for a value of c that is between 0 and 1. All right, that's our summary. So you might have filled this out on your own. I mentioned you could. If you did not, this is just all of the information from the previous pages just put into a summary here. You have a function f of x, adding or subtracting k units. Well, if you're adding, you're going to move your function up k units. If you're subtracting, that function is going to go down k units. Inside the function, adding will go to the left, subtracting will make the function shift to the right. If you're taking the function and multiplying it by a negative in front, it's an x-axis reflection. If you're multiplying by a negative inside the function, then it's a y-axis reflection. Questions on this page? I know it's like we kind of went over it, but it was 5 days ago. You know, this window covers up your faces, and that makes it even harder for me. There, and I can see some of you again. And then the last part of this summary has to do with the stretching and shrinking. When you take a function and you multiply it by some constant a, it's going to be a vertical stretch if a is greater than 1, and a vertical shrink if a is between 0 and 1. If you multiply inside the function by some constant a, it's a horizontal shrink if a is greater than 1, a horizontal stretch if a is between 0 and 1. As long as you have all of that information summarized together in one part, hopefully your notes will be very helpful to you. I had mentioned before, for your exam, you will be able to use your notes as long as you know where everything is. Hopefully you've taken good notes and that will be helpful to you. So let's go ahead and use this information to create some functions. Example 1, create a function that would move the graph of f of x equals x squared, right 4 units and up 1 unit. Now I want you guys to do this, and then I'm going to write down what the answer is in like, a minute and a half after I finish attendance. So I think you can do this just fine. see. All right, Simon, did you forget part of this answer that you are writing down here? Simon says x minus 4 quantity squared. Let's call it g. Does this function move your... Oh, okay. Does this function move your graph to the right 4 units? What do you guys think? What do you people think?
Yes.
Yes. Oh, great. People are answering me like verbally. This is amazing. Okay. Yes, I agree. This one does move your function to the right 4 units. If I want to take it up 1 unit, oh, Simon says we should add 1 to it. Yes. Yes. Very good. Sorry, I'm looking at the chat and looking at you guys. There's all kinds of different stuff going on here. If you want to move it up 1 unit, you have to add that 1 to it. So that minus sign inside the function is going to shift your graph to the right 4 units. When you add 1 outside of the function, you're shifting the graph up 1 unit. Wonderful. Questions on number 1? The main thing to watch out for here is just to make sure that you're not thinking that right is plus, because right is minus. Okay. Create a function. Oh, this should say that would, not what would. That would reflect the graph of f of x over the x-axis. So when you're trying to do this, you can always refer to your cheat sheet, but you're going to get used to doing this after a while and you won't need to do that. And you're thinking, reflection, what is an x-axis reflection? Well, an x-axis reflection is when I take the function and I multiply it by a negative. So the negative should be in front of the function. So all that is needed to create that x-axis reflection here is one tiny little change. Don't call your function f because this is f. Give it another name. It doesn't have to be g. It can be any other name you want. I wouldn't use e or I, but I guess technically you could. Let's say g of x is negative absolute value of x. And by just making that function negative, inside the function, you get that x-axis reflection. Now, if you wanted the y-axis reflection, you'd put the negative sign inside the bars. Questions about example 2? Okay. Number 3, create a function that would vertically stretch the graph of f of x by the equals the cubed root of x by a factor of 3. Now, again, you can look at your cheat sheet if you're not sure, but you know that a vertical stretch is created when you have a value of a that's greater than 1 and you multiply the function by a. So if all you're doing is a vertical stretch, and that's, by the way, the most common kind, a horizontal stretch is a thing, but you mostly only see it in this section. You're not going to be using a lot of horizontal stretching and shrinking, but you will see a lot of vertical stretching and shrinking. So to create a vertical stretch, you're going to take that factor of 3 and multiply it by your function, which is the cubed root of x. Okay, so to do number 4, I'm going to give you an order of transformations because you're going to find that's very helpful to you, because you're going to find that if you do the transformations in a different order, you're going to end up with a different answer. These transformations cannot just be done willy-nilly. You can't just pick which one you want to do first. In your text, this would be found on page 292. I'm going to summarize it for you right here. Page 292 gives you an order of transformations. This is very important. If I were you, I'd put a big star by it in my notes, maybe even highlight it. Maybe I should get my highlighter up. Let's see if these highlighters even work. This is very important. Kind of. Order of transformations. Focus. Okay. The first transformation that should be done is the horizontal shift, if there is one. If there is a horizontal shift, that goes first. The second one will be any stretching or shrinking, whether it's vertical or horizontal. That will be done after any horizontal shifts. The third one is reflections, whether it's x-axis or y-axis. And then the fourth one will be any sort of vertical shift. So the vertical shift goes last. I forget the order to these all the time. So don't feel like you need to memorize these. As long as they're in your notes and you have a star by them and they're highlighted so you can find them, they're important, but I don't use these all together at one time often enough to remember what order they go in. Creating functions anyway. All right, so let's go ahead and use the order of transformations to answer the question for example 4. If 9, -2 is a point on the graph of some function h of x, what point would be on the graph of negative h of x minus 3 plus 2? So what we're going to do is we're going to take this 0.9, -2, and we're going to transform it. And if you would like to draw a picture, you might find that to be very helpful. I tend to think about this more algebraically. It's kind of up to you, but you can sort of see what's happening with this point and follow it along. 1, 2, 3, 4, 5, 6, 7, 8, 9, -2. So your original point, 9, -2, is right down here. First, let's talk about the changes that are happening. I think it's really important to be able to look at what's going on in the function and first to label the changes that are occurring. And if you'd like to label them by first going down your list, that's fine, because that's the order in which we're going to have to apply the transformations. So first, a horizontal shift would occur. So you're going to look at your function and determine whether or not there is a horizontal shift. And I feel like most of us are pretty good at recognizing these at this point. And you'll notice that, yes, we are indeed adding or subtracting inside the function. And since we're taking x minus 3 inside the function, then it must be that we have a horizontal shift. And since it's a minus, we're going to go right 3 units. And we'll go ahead and talk about what happens to that point in a minute. I just want to make sure that we are comfortable with starting to list out the changes that are occurring here. So that's the first one. Then you're going to look for any stretching or shrinking. When you're looking for stretching or shrinking, you're looking at whether or not we're multiplying this function either in front of the function or in front of the x by any constant. This is just x. It's not like 5x or 1/2 x. So there's no horizontal stretch or shift. And because you just have a negative in front, don't think about this as being -1 in this case. It is, but the 1 doesn't matter. If the coefficient's 1 or -1, that's not going to stretch your function at all vertically or shrink it vertically. So you don't actually have any stretches or shrinks going on. The next thing is reflections. So that clearly we have. When you see the negative sign in front, that's signifying to you that you have a reflection. We already used this one today, back up here in example 2. An x-axis reflection is the kind that has the negative in front of the function. So we would say that we have an x-axis reflection. Well, I don't know how I'm spelling reflection here, but something weird happened. So we've taken care of the x minus 3, we've taken care of the negative h, and now we just need to think about the fact that we're adding 2 to the function, and that's a vertical shift up 2 units. So let's go ahead now and look at our point and determine what happens to the point as it goes through these changes. Does anyone have a question about the 3 changes that we listed out here? Okay, wonderful. If you do have a question, then you gotta pipe up. All right, so we're looking at our point 9, -2. If you feel like you're very visual and you need to kind of just move this point around physically, be my guest. The point's at 9, -2. If it's being shifted to the right 3 units, then it's going to be at 10, 11, 12, -2. It's going to go this way. So that's your horizontal shift to the right 3 units. If you feel more comfortable doing this from an arithmetic point of view, think about the fact that you have this point 9, -2. And if it's going to the right 3 units, that means the x coordinate is going to increase by 3. So you're going to just add 3 to the x coordinate, and that gets you to 12, -2. I've had students who do everything visually and graphically, and I've had students who just do everything by manipulating the ordered pair. You do whatever you're most comfortable with. But either way, you end up at 12, -2 after you make that first horizontal shift. When you make your x-axis reflection, remember that you are just going to be reflecting your new point over the x-axis. So that means when it gets reflected, it goes up this way and it swings over the same number of units up as it was down. It's not moving anywhere to the left or right. It was 12, -2. Maybe I'll label these ordered pairs. Maybe that's more helpful. And now it's going to be 12, +2. So we started out here. We moved to 12, -2. And now we're at 12, +2. And again, if you're just manipulating these ordered pairs, you will know that an x-axis reflection is just going to change the sign of the y-coordinate. The x-coordinate is not going to change. So we're going to take our coordinate and switch it over to 12, +2. And we have one more shift to do. Before I do that, does anybody have a question? Okay. This is unfortunately one of those things where if you were to just look at the notes later, you'd be like, what the heck was she doing? Whereas if you watched the video, it would be a little bit more clear. It's hard to see all this after it's all been done, but when you see it developed, it seems a lot more intuitive. All right, so the last thing is a vertical shift up 2 units. So when you shift up 2 units, now instead of being at 12.2, you are at 12.4. So you're going up to 12.4. My labeling is terrible here now. Clearly, I didn't anticipate that. A vertical shift up 2 units is going to shift y up. And I'm adding it to the wrong coordinate now. Awesome. Here's my labeling. So here's my vertical shift. Focus. Let's see if I can make it focus. Now we are at 12.4, which is your final answer. So I'm going to see if I can put some of those on the homework for you. I think those are really good problems. Expect to see something like that on a test, just one, but something like that. You got to remember your test has to be a little bit more non-traditional because of the fact that you're all taking it online and you're not being proctored. And I'm getting so many emails from teachers being like, I have my students set up 2 Zoom views and I make them put their phone in a mug in front of me and I do this and I do that, and it sounds really, really stressful. I don't want to have to watch 28 of you like a hawk for 2 hours. I'm going to do the best I can to make an assessment so that I can tell what you know and that it's still very clear to you without giving you something that you can pop into a website, which is technically cheating. Oh, that being said, make sure you're showing all of your work. Any questions on example 4? Okay. All right, so the last one. And I want you guys to do this, and then we'll discuss. Create a function that would move the graph of f of x equals x squared left 2 units, down 5 units, shrink it by 1/2, and reflect it over the x-axis. Go. So every time I teach this example, somebody always asks me what kind of shrink I'm talking about. They always say, you didn't say what kind of shrink. You didn't say if it was vertical or horizontal. But I did tell you I was shrinking it by 1/2. Do I have to say whether it's vertical or horizontal? No, because if I'm doing a shrink by a factor of 1/2, the only way I can shrink would be vertically. 1/2 is between 0 and 1. So I can't do a horizontal shrink by 1/2. I can only horizontally shrink by numbers that are greater than 1. So it must be a vertical shrink because of the fact that it's 1/2. So let's note that. Must be vertical. Okay, so you're creating this function. I'm going to call mine g. I know that's boring, but that's what I'm going to call it. It's x squared. I'm shrinking it by 1/2 vertically, so I'm going to multiply in front of the function. And if it's being reflected over the x-axis, then I'm also going to apply a negative to the front of the function. So this negative sign creates your x-axis reflection. The vertical stretch means I'm going to multiply in front of the function by 1/2. Oh, shrink. Sorry, I said stretch. I'm trying to alleviate confusion, and then I said the opposite of what I meant. Vertical shrink. And now we'll take our function x squared, and instead of calling it x squared, since we're shifting it left 2 units, we will add 2 inside the function. I hope you guys didn't subtract 2. Make sure you add 2 and square the quantity. We're inside the function now. And then down 5 units, outside of the function, we're going to subtract 5. So here we have left 2, and we have down 5. This is also a really good problem. I could do something like number 5 instead of number 4. I don't know. They're both awesome. That's it for 2-5. Any questions there?
why do we have to square it?
Oh, because remember it used to be x squared. So we don't want to lose the fact that we have a quadratic function. But now in order to shift it to the left or right, we need to add or subtract inside that original function. So instead of just saying x squared, well, I have to say x plus or minus a quantity squared. Is that clearer? Okay. Any other questions here? I know there's a lot going on in this example. Okay. So that was 2-5. Nothing super crazy. I'll definitely be doing some things on the test where you're just doing one transformation at a time. I might just give you a generic function and have you manipulate it, kind of like the examples that you saw here, especially 4 and 5 I thought were great because they were pretty generic functions. But also, you know, just stuff like giving you a graph and asking you to, you know, perform some sort of graphical changes to it. Something like that would be a really good test question too. Even like this, where you're doing two different things to the graph. Okay. Now, 2.6. You should all have these notes now. If you do not have these notes and you don't have a printer, email me and I'll see if I can take a trip into ECC and get them all copied for you at least, because copying out all these notes on my home printer was a lot. But let me know if you didn't get the notes and you don't have a printer. Let me know. I think most of you should have gotten them by now. All right, so in 2.6, we're going to talk about combinations of functions and composite functions. A lot of these combinations you'll find are review from algebra. The composite stuff, I'm not sure that you did before in algebra unless you had a class similar to this. In high school, you might have done some of this sort of thing, but it might have been a while for some of you. All right, so finding the domain of a function. If you took Math 98 at ECC, we definitely did this in Math 98 when we were in 2 different sections. We talked about this quite a bit. If a function f does not model data or verbal conditions, its domain is the largest set of real numbers for which the value of f of x is a real number. Exclude from a function's domain real numbers that cause division by 0, and real numbers that result in a square root of a negative number. So right here, you're being given 2 things to watch out for. Division by 0, that's one big red flag that you're looking out for, and a square root of a negative number. That's another big red flag that you're looking out for here. So you're going to be given functions, and you're going to be asked to find the domain of that function. If your function does not have variables in the denominator, then you don't need to worry about dividing by 0. You have to have variables in the denominator in order to have this problem. If your function doesn't have a radical in it, then you don't need to worry about taking the square root of a negative number. These are the things that will cause you problems. So when you're looking at number 1, you have f of x equals 5x plus 3. This is a polynomial function. Polynomial functions don't have any variables in the denominator. They don't have any rational exponents, meaning they don't have any radicals in them. Because they don't have either of those things, then you don't actually have any issues that cause problems for your domain. What you're thinking about here is, can I let x be any number I want? Is there any number for x that causes a problem? And if you don't have a variable in the denominator, you don't have a radical, then you're not going to have any issues. You can choose any value in the world that you want for x. You can choose x equals 5, X equals 1/5. X equals 1,000,000. X equals the square root of 5. X equals pi. Does not matter. You can evaluate any real number for X, and you will not end up getting a function that is dividing by 0 or taking the square root of a negative number. Because of that, your domain is all real numbers. Now, you're going to have to write your domains in interval notation. So if you say all real numbers, I mean, it's nice that you know that, but that's really not the answer that I'm expecting to see. What I'm expecting to see from you is interval notation. And the way that you would denote your answer as including all real numbers is to include any value of X such that X goes all the way from -infinity to +infinity, and it doesn't exclude any values in between. So anytime you have a polynomial function where you don't have any variable in the denominator, you don't have a radical with a variable in it, all real numbers. On a test, if you said all real numbers, I might give you like a point, but then you'd probably lose about 3 points on your interval notation, because that's really what I'm asking you to find here. Are there any questions on number 1? Okay. Number 2, we have f of x equals x squared plus 8. Again, you don't have any situation where you have a variable in the denominator. You don't have any radicals that have variables in the radicand. If you don't have either one of those, you can't find any value of x such that you'll be dividing by 0 or taking the square root of a negative number. Again, your domain will include all real numbers or any values of x such that x goes from negative to +infinity. So the first one that we have here where we really need to look out for values that our domain should exclude is number 3. Now in number 3, you have a rational function, which means that you have a variable in the denominator. Right off the bat, you have a variable in the denominator. You're going to have some issues with your domain. Think about what happens if, for instance, x equals 2. 2 squared is 4. 4 minus 4 is 0. We cannot divide by 0. We can have 0 in the numerator, but not in the denominator. That's undefined. You cannot do it mathematically. So right off the bat, we've thought about a number that we should exclude from the domain. But I don't want you to be guessing here. I want you to actually show me the work that you went through to find these values. When you're trying to find values to exclude from the domain, you're going to take your denominator and set it either to equal 0 or not equal 0. It doesn't matter as long as you're solving for the denominator being equal to 0 and you exclude the values, that's fine. I just show it not equal to 0. And then you're going to solve this equation. Now you can use the square root property here, and that's fine. If you use the square root property, you must remember to take a plus or minus when you take the square root. Otherwise, you can factor this into the difference of 2 squares, which is the way that you solved these when you were in your previous algebra class. But we can go ahead and solve this equation by adding 4 on both sides and making sure that x squared cannot be equal to 4. And then using the square root property, we can isolate x by taking the square root on both sides. Don't forget your plus or minus. And again, this is a step you don't need to include. All you really need to say is that x cannot be equal to plus or minus 2. Because in the same way that 2 causes an issue for your denominator, -2 will do the same thing. -2 squared is +4. 4 minus 4 is 0. That's a problem. Now, just finding these values is half the battle. The other half of this battle is writing your answer in interval notation. You're going to need 2 separate intervals here, actually 3 separate intervals. Because what we're going to do is we need to find a way to talk about the numbers that we can use for x, what values are in the domain. What I can do here is I can use any value heading up from negative infinity as long as it doesn't include -2 all the way up to 0. To do that, I'm going to start my interval at negative infinity, and I'm going to stop it as I approach that first value that causes us a problem. And the first value that causes us a problem is -2. So I'm going to look at any number between negative infinity and -2. Now, it's really important we understand that the -2 gets a parenthesis, not a square bracket, because we cannot include -2 in the domain. That would be the worst. We have to make sure that we go all the way up to -2, but not include it. Then we're going to pick up that interval because any value in between -2 and 2 is fair game. We can use that in our function, and it's not going to give us 0 in the denominator. When we include more than one interval, you're going to use a union. We talked about this briefly the other day. Use the union symbol to connect the two intervals. And you're going to pick up where you left off at -2. Make sure you are using a parenthesis, not a square bracket. And then you're going to go all the way up to the next value that causes you a problem, which is +2. And what this means is that any value between -2 and +2 is okay to use. You can use x equals 1. You can use x equals 1.2. You just can't use -2 or 2. And then you're going to pick up your interval one more time, use another union symbol, and then pick it back up at 2 and go all the way up to positive infinity. This is how you denote values that are included in your domain. I am going to start turning on the lights here because it's getting crazy dark. Let's see. I wonder if I can get my husband to agree to get like a candlelight installed over here. I doubt it, but it would be really nice. Does anybody have a question on example 3 or the domain? Wonderful. All right. You will see some domain questions on your exam. I know that in the previous algebra class, for some reason, when I ask on a test for students to find the domain of a function like this, they totally blank and they leave it blank and lose a lot of points. It's not a really hard thing to do. I think they just forget what it means to find the domain. Hopefully there'll be a little bit more of an emphasis here for this class so that you're aware of what you're supposed to do. Number 4, this is the other major violation as far as the domain is concerned. You have a radical function. Now, it's not just about having a radical in the function. The issue is that you have a variable inside the radical. If you just had the square root of 10, well, that's a constant. You wouldn't need to worry about that. But because you have a variable here, that means that you could introduce some value x that would end up making this function not a real number. Like, for instance, imagine if x was 11. Well, 10 minus 11 is -1, and then you're taking the square root of -1, which you can't do, at least as far as looking for real valued solutions. So what you're going to do is you're going to force your radicand to be greater than or equal to 0. Because you can take the square root of 0, that's okay. So if 10 minus x is 0, no big deal. We just can't have it be less than 0. So we're going to take the radicand and force it to be positive or equal to 0, and then we'll solve for x by solving this inequality. And we're going to get a range of values here that we're going to include. Now, if you would like to add x on both sides, that's fine. I'm going to do this 2 different ways because I'm assuming half of you are going to do it one way and half of you will do it another. If you add x on both sides, then you end up with 10 is greater than or equal to x. Now, you can always switch the direction of your inequality as long as you switch the entire inequality. So you could say that x is less than or equal to 10. The less than or equal was pointing to the x. It's still pointing to the x if you switch it around. This is saying that we need to choose a value for x such that x is less than or equal to 10. So something like 10, 9, 8, 7, or even a negative value would work. If x was -1, well, 10 minus -1 is 10 plus 1. So no problem there. If you were to solve this inequality, I'm going to write it one more time. If you were to solve the inequality by subtracting 10 from both sides, I just want to caution you to this, just because a lot of students forget how to do these. You'll end up with -x is greater than or equal to -10. To solve for x, you're going to have to divide both sides of the inequality by -1. Whenever you multiply or divide an inequality by a negative number, you need to switch the direction of the inequality symbol. It's probably been a while since some of you have done that. So that's fine. You can divide out by -1. X divided by -1 is x. But anytime you divide both sides of an inequality by a negative number, you have to switch the direction of the inequality. So you get the same answer, just in a slightly different way. You choose whichever way you like best. I always see students doing both of those things. And again, if you gave me this information, that would definitely give you some partial credit. But your instructions will explicitly state on your exam that I would like your solution to be written in interval notation. So that means you need to write this by showing me values of x that are less than or equal to 10. If you're looking to create that expression in interval notation, well, think about what that means. Any value of x that's less than or equal to 10 is included. That means any value all the way down to -infinity is a value that we could substitute for x in order to get a real valued solution here. So we're going to choose values starting all the way as they approach -infinity and heading all the way up to 10. Now, we made a really distinct point in the last example to use parentheses instead of square brackets. In this case, we can include 10 because taking the square root of 0 is okay. We're going to use a square bracket to signify that that value can be included in the domain. Any questions on number 4? All right, no questions? I only see like 2 of you right now, so. But the 2 of you I see look like you're doing okay. On page 302, there's a question about whether you should simplify a quotient before finding its domain. The answer is no. And I'm going to add an example on here just because I think it's a really good question and it happens all the time. So I want to make sure we understand. Example 5, let's just pop it on here. Let's look again at example 3, but consider what would happen if the numerator was something like x plus 2. Now, if that was the case, the simplification would occur if you decided to factor in the denominator. Now, if you factored in the denominator, you would end up with x plus 2 times x minus 2. This is a difference of 2 squares. If you're not sure, multiply those 2 binomials together and verify that you get that special product x squared minus 4. Now, what students try to do is they decide, oh, well, look, I can cancel out a factor of x plus 2, and I can rewrite the function as 1 over x minus 2. Now, yes, technically that's true. You can write an equivalent function. However, as far as finding the domain is concerned, these two functions have different domains. So you should not simplify first. Unfortunately, I tested out my calculator today and everything was working beautifully with my lighting situation. But now here we are again with the lights on and we can't see again. It's very unfortunate. Such is life. But if you look at these two functions, g and our new function, whatever we created, for G, I did email her, by the way, about getting an emulator, and I have not heard back, so we'll see. X plus 2 divided by x squared minus 4. That is the original function. The new one that we created was 1 divided by x minus 2. Now we can look in the table to talk about the domain of each function. And if I were to go to the table here in my calculator, notice that on the values of -2 and +2, the first function has errors. So for y sub 1, when x is -2, y sub 1 gives me an error. And when x is +2, I get an error. For the second function, the new one we wrote, we do get an error when x equals 2, but when x is -2, we get a value. What we did there was we got rid of a discontinuity in the graph. However, we still have a domain issue. When you graph these, the graphs are going to look the exact same. They're just going to graph over each other. So the graphs will look exactly the same. The difference is that your new graph fills in a hole. And we're going to talk about this a little bit later when we get into chapter 3. We'll talk about discontinuities in our graphs and what it means to have either some sort of a vertical asymptote or a hole. We're going to get to stuff like this where it will help to simplify it, and we'll have to do that first. When you're finding the domain, however, you don't want to end up losing values that should be excluded. So I'm going to make a note here. Don't do this when finding the domain. So the answer to the question, should I simplify a quotient before finding its domain, is no. Don't simplify it first. Take the function as it is, work with the function you have, and look at the domain from there. Notice that this domain is the same domain that you would have for example 3. So your domain here would go from -∞ to -2, from -2 to 2, and from 2 to infinity. Same as number 3. Any questions on, oh, you know what, I should have called this 5A because we already have a 5. I'll call it 5A. Any questions on that example that I added? Okay. Wonderful. And let's look at a kind of rational function that maybe you haven't seen in a while where factoring is required for number 5. So for number 5, you do indeed have a situation where you have variables in the denominator. As soon as you have any variables in the denominator, you need to isolate that denominator and verify. Make sure that you find values of x that are going to make the denominator 0. When solving this equation, it is a very common error that students add 64x to both sides and divide out the x's. Don't do that. You're going to lose a solution. You must factor out that x. You cannot divide both sides of an equation by a variable. You're going to lose a solution. Take out the x, and that leaves you with x squared minus 64. And again, you have a situation here where you have a difference of two squares. X squared and 64 are both perfect squares. You learned a factoring formula for that in your previous algebra class. You have x plus 8 times x minus 8. And now you end up with three values that you need to exclude from the domain. One of them will be -8, the other is +8, and another one of them is going to be 0. So if it's been a while since you've used that zero factor property, I will remind you now of how to use it. You're going to take each factor and set it not equal to 0. So you have x cannot equal 0. Subtract 8 and you'll get x cannot equal -8. Add 8 and you'll get x cannot equal +8. And again, you're going to have to write this in interval notation. You're going to have 4 different intervals for this one. You're going to start out at -infinity and go all the way up to -8 with no problems. And then you're going to go from -8 all the way up to 0. Take 0 up to +8 and +8 up to infinity. That will be the domain for number 5. All right, questions on number 5. All right. Let's talk then about combining functions using the algebra of functions, specifying domains. Let f and g be two functions, the sum f plus g, the difference f minus g, the product f times g, and the quotient f divided by g are functions whose domains are the set of all real numbers common to the domains of f and g. This is just saying d sub 1 and the intersection of d sub 2. Don't worry about the notation. That's probably why I never went through and fixed it in the notes. Your sum of f plus g is just f of x plus g of x. The difference f minus g is f minus g. The product f times g is just f of x times g of x. And for the quotient, same thing. F over g is just f of x divided by g of x, making sure that g of x is not going to be equal to 0. So we're going to perform the indicated function operations, and then we'll find the domain of the resulting function. And normally students don't have any trouble finding these combinations of functions here, but I'm going to go through them with you, especially adding the functions together. Usually that's super straightforward. When you're taking f plus g, you're just going to take your function f, which is 4 minus 5x, and then add your function g, which is -8x plus 5. If you want to use parentheses, fine. If you don't, doesn't matter because you're adding and you never have to use parentheses when you add. I know it looks weird to say plus a negative, but it's fine. Now you're just going to combine like terms. You have -5x plus -8x, which gives you -13x. Then you have +4 plus 5 equals 9. And that's how you add two functions. I will caution you that when you're subtracting two functions, you must use parentheses because that minus sign needs to get distributed to the terms that follow it. So when you take f minus g, start out the same way. Take your function f, which is 4 minus 5x. Now when you subtract off g, you're taking minus and then put that function in parentheses. Don't forget that your 8 is still negative, so you're taking minus and then that whole quantity negative 8 plus 5. I know sometimes students will practice this a lot and they'll start to shortcut and they'll just immediately just switch the signs on these two terms and move forward. That's fine, as long as you remember to account for it somewhere. That's what matters. Now let's go ahead and remove the parentheses. To do that, we're going to distribute this negative sign or this minus sign into the two terms that follow it. So we have 4 minus 5x plus 8x minus 5. Now, once you've removed your parentheses, you can start to go through and combine like terms to simplify the expression. So we'll have negative 5x plus 8x, which is 3x. And then 4 minus 5 is negative 1. So you have 3x minus 1. Just be careful. I said it like 4 times because it's a very common mistake that students forget their parentheses. And then they end up screwing up the sign on one of the second terms, and then their answer is off. Because really, it's not supposed to be a hard problem. So try not to lose points on something that's not supposed to be a hard problem. This is your solution. Questions so far? Okay. I can see one person and I can sort of see another person like in the darkness of night. So feel free to turn on your cameras and it will help me to feel like there are other people on the end. More than just those two people. Okay. Next, we're going to find f times g. Now, a lot of times that's just going to say fg. If there's no symbol in between them, it means you're multiplying. So we're going to take f and multiply it by g. And for this, we're going to have to remember how to FOIL. You could technically use distributing here. It's pretty much the same as FOILing, up to you. So I'm going to take f and I'm going to multiply it by g. I'm going to use parentheses around both. And I'm not going to put a symbol in between them because I'm multiplying them together. Remember when you FOIL, you're doing first, outside, inside, last. We haven't done a ton of FOILing in here. Oh my gosh, I'm spelling outside with 2 O's. Clearly, I don't do this acronym thing a lot. Okay, first, outside, inside, last. So your first terms are going to be 4 times negative 8x. So we should have negative 32x. Make sure to include that negative sign in there. Your outside terms are 4 times positive 5, which is plus 20. Your inside terms are negative 5x times negative 8x. So multiply those two negatives together and the product will become positive. 5 times 8 is 40. X times x is x squared. And those are your inside terms. And then for your last terms, we have negative 5x times positive 5 is negative 25x. Now, don't leave it like this. It's almost done. You have a constant term here. You have a quadratic term here. And then you have 2 linear terms that just have x to the first power on them, and we have to combine those. I like to write these in descending order, which means putting the quadratic term first. And then we have negative 32x minus 25x. So 25 and 25 is 50, add 7 more and you get 57. So minus 57x plus 20. Now, again, this is not supposed to be some really hard problem. It's one of those problems where one little tiny sign will be off. And because the sign was off, the whole thing's going to end up being wrong. If you show me all your work, which I'm going to request that you do, I should be able to catch something like a little tiny sign being off. Like if you write this as plus 25x instead of minus, then I'll be able to see like, oh, I see they took negative 32 and added it to 20. That's why they have the wrong middle term. Got it. But if you just write me an answer and I just see one term that's wrong, I can't give you the partial credit for what you did do correctly. You have to show me your work. All right, let's do D. We're going to take F and we're going to divide it by G. So our function F is 4 minus 5x. And our function G is negative 8x plus 5. The nice thing here is that in this particular situation, that is all you have to do. You don't have anything else to do for this one. Michael, what about on the homework that was due for tonight? How would we show our work with graphs? Michael, are you talking about 2.2 or 2.5? Like shifting the graphs around? Because I think you're talking about 2.5. Yeah, 2.5. So for 2.5, I'm going to ask you some specific questions. So you're right that for 2.5, I don't actually want you to do tables of values and plug in values for X and plug in values for Y. If you do that for 2.5, I'm going to be mad because I want you to use transformations. So yes, for 2.5, the way that I'm going to write the instructions is that I'm going to try to elicit information from you. So for 2.5, even though I'm going to have you do some graphing, I'm going to ask you questions like, list out the transformations that are occurring. So you're going to tell me this graph gets shifted up this many units, this graph gets, reflected or not rotated, reflected or stretched or shrunk by a certain value. And as long as you state those changes that are occurring and then you make those changes in your graph, to me, that's enough work. I'm just thinking, okay, if he knows he's supposed to shift the graph up 5 units, that's what he did. Awesome. I don't need to see any more. Does that answer your question about showing work for 2.5? Okay, cool. Yeah, so I've taught this class a lot of times. I've gotten pretty good at figuring out what exactly I need to tell you to do to elicit the information that I need. Because I've always ended up in the past with a situation where my instructions haven't been clear enough, and then I've had to go back and rewrite the test for the next time to make sure I say this, make sure I say that. So the instructions are going to be pretty clear, just from having had the experience of not being clear enough in the past. So you should be good there. And when you're taking the exam, if something is not clear, do feel free to pop up and ask, because I will be on during the exam, so that in case something is not clear or you're not sure what I'm looking for, that you can ask. I mean, I can't obviously give out like hints or anything, but I can clarify if you have a question. Okay. So do we have any questions about G, or how do we know when we're done? Because sometimes it seems like students are like, wait, how do I know if I'm done? How do I know if there's anything else to do? We're going to come to a question here. Probably we'll cover it next time, where you're going to see a complex fraction, and you're going to see an example of what happens when you're not done. but here, we're done. Given functions f and g, determine the domain of f plus g. Okay, so for this one, I'm gonna take you back a little bit to your algebra days. F plus g in this situation might look super straightforward, and it sort of is. You're taking the function f, and you're adding the function g, but you can't leave it like this. You're going to have to combine this as one fraction when you're entering your answer in MyMathLab, and it will state that in the directions. So when you combine this as one fraction, remember that they each have to have a common denominator. If you don't remember how to do this, feel free to stick around for the office hour. It's also in chapter P of your textbook, but I'm also going to show you right now. You can create a situation where you have a common denominator by taking those first terms and multiplying by x minus 9 over x minus 9. Remember that to add these two fractions, you have to sort of unsimplify them. And don't cancel because you created that on purpose. But what you're looking for here is a situation where you have a common denominator. And as long as you have a common denominator, you can add and subtract in the numerator. You guys spent a lot of time doing this if you took Math 98 at ECC. It was in 7.4. Once you have a common denominator, you can go ahead and add in the numerator. Now, in order to add in the numerator, you're going to have to simplify in this first numerator by multiplying. So you're going to FOIL. 2x times x is 2x squared. The outside terms are 2x times negative 9. The inside terms are negative x. And the last terms are plus 9. And then don't forget, you still have a plus 2 from this second numerator. And then the last thing you have to do is simplify this one more time by combining like terms. So this is a review from your previous algebra class. Hopefully you will find it helpful just to have seen me do it instead of just getting a shock on the homework if it pops up. So combine your like terms and you end up with 2x squared minus 19x plus 11 divided by x minus 9. So this is the expression f plus g. And now the domain of f plus g is just going to be the domain of this expression. You don't have to actually write out x minus 9 cannot equal 0. I think this is one where just by looking at it, because it's linear, you can tell that if x is 9, 9 minus 9 gives you 0 in the denominator. So if you already know that x cannot equal 9, that's fine. You can make a note of that and then write your domain in interval notation by excluding 9. Here's your domain. And we'll do something sort of similar for number 8. Are there questions on number 7? Okay. Wonderful. So for number 8, we're going to find f divided by g. To do that, we're going to take the square root of x divided by 4x minus 1. Now, in this case, there's nothing else to simplify here. Your answer is already one term. We're just going to go ahead and find the domain of this function. Now, we're going to have to be careful here because whatever value is in the domain in our denominator, we have to also check it in the numerator. So you have sort of a double whammy because you have a rational function where you have a variable in the denominator, and then you do have a radical that we need to look out for here. So let's go ahead and focus on the denominator first. Make sure that the denominator is not going to be equal to 0. And then go ahead and add 1 on both sides and divide by 4. So as far as our denominator is concerned, x cannot be equal to 1/4. But Watch out because you still have a radical in the numerator. Normally when we look at the domain, we don't really care about the numerator, but when it's a radical in the numerator, we do care. We have a situation here where x has to be greater than or equal to 0. It must be the case because if we're going to take a square root of a number, it has to be greater than or equal to 0. So if we know that our value of x has to be positive, then I know that the smallest domain, the smallest value we can have in the domain is 0. I can't have any number that's less than 0 in our domain. And then the next number that causes me issues is 1/4. I can go all the way up to 1/4 with no problems. And I cannot be equal to 1/4 because that'll make my denominator equal to 0. And then once I get past 1/4, I get over that hump, I can choose any value I want all the way up to positive infinity. Make sure that infinity always gets a parenthesis, not a square bracket. So a little bit more thinking involved for the domain on this one, just because you had two different things going on. Questions on the domain there? I know you guys have to be faster with your chat if you have questions, because I know sometimes it takes longer to type something out than to raise your hand in class and ask. So I'm trying to give you ample time. I'm skipping number 9 because it's actually a really crazy problem. And I'm not going to give you anything that crazy on your test. So I have already marked that one for skippage. But let's talk about number 10. Find the domain of f over g when f is 7x squared minus 9x and g is x squared minus 4x minus 7. So first we need to find f over g, and then we'll talk about finding the domain. So f over g is 7x squared minus 9x divided by x squared minus 4x minus 7. And that is our definition for f over g. And again, this is already just one fraction. So we don't really have anything else to simplify here. The work will be in finding the domain. So what we're going to do for the domain, we don't have any radicals to worry about. The only thing we're going to have to worry about is the expression in the denominator. We're going to go ahead and take that denominator and force it to not be equal to 0. And we're going to exclude any values of x that make it 0. To do that, we're going to have to solve the equation. Now, if you can solve it by factoring, do that. The one that we looked at on the first page was a difference of 2 squares. You don't have that here. This is a quadratic equation. If you can factor it, fine, but you can't find any numbers that multiply to -7 and add to -4. So you can't factor this one. You're going to have to use the quadratic formula. So we're going to make sure that x does not equal negative b, -4 is +4, plus or minus the square root of b squared minus 4ac, all divided by 2a. This is perfect. We're going to finish this one and talk about composite functions and how they relate to inverses on Wednesday. Okay, make sure again that you have parentheses around b squared. So we'll have 4 plus or minus the square root of -4 squared is +16. And then we have plus 4 times 7 is 28. Be careful with your signs here. You have a negative times a negative, which gives you a positive. Continue to simplify this. 16 plus 28 is 44. And then you're going to simplify this even further because you're noticing that 44 contains a perfect square factor. 44 is 4 times 11. And again, I'm including a little bit more work here because I want it to be really clear what I'm doing. And I know some of you are still struggling with simplifying these, so I want to make sure it's really clear. I'm going to take the square root of 4 and simplify that to 2. So going from here down to 2. And then because I have a 2 in common in every single term, I'm going to divide each term by 2. 2 divided by 2 is 1. 4 divided by 2 is 2. And that leaves me with 2 plus or minus the square root of 11. Now, if you get all the way to the bottom and you don't remember what we were originally trying to do, we were trying to find values of x that were excluded from the domain of our function. So we're going to exclude these 2 values of x. Don't give me decimal approximations. These are exact values. So they're numbers. Just think about them as being decimal numbers, but don't write them as decimal numbers. What we're going to do is write our domain to exclude these 2 values. So I'm going to start out at negative infinity. And then I'm going to go to the first number. The first number is the minus variation. 2 minus the square root of 11 has to be smaller than 2 plus the square root of 11. So I'm going to exclude that value first. Then I'm going to pick it up from there. And I'm going to exclude the next value. Any value in between 2 minus root 11 and 2 plus root 11 is okay. I just can't use either one of those values. And then I'm going to pick it up again at my 2 plus the square root of 11 and send it all the way to infinity. Sometimes it helps students to think about the fact that if you're excluding 2 values from your domain, you're going to have 3 intervals. So you're always going to have 1 more interval than you have values that you're excluding. Okay, I'm going to post the recording on YouTube as always. I haven't decided if I'm going to keep posting the notes on D2L just because I feel like I want you to be doing something on your own, and I don't want you to just be sitting there doing nothing and then printing out my notes for reference on the exam. Now that you all have notes that you received in the mail, I shouldn't have to keep posting mine on D2L. If you miss class, you can always go to YouTube and watch the class, and that'll be a motivator for you to do so. So I will post what we finished out of 2.5 and finish that off. I've been really diligent about putting those YouTube links up. Those you can find in D2L. Under content, there's a section called YouTube class links. You can watch any of our classes there. It says what we covered that day in brief and what the date of the class was. So it should be pretty clear. I will be on for another like 15 minutes. So feel free to stick around if you have questions, and feel free to email me. And like I said, if you emailed me your homework before 6 and then I asked you to upload it to D2L and you didn't get a chance to do so because now it's past due, I'm going to go back through there and I'm going to extend the due date for you. But I still want you to do it tonight. I'll probably just extend it to like midnight or something. That's what I'll do. And I'm going to put up some homework. And then I'm going to put up a review assignment. And then I'm going to put up a key to your graphing homework. I'm going to be very busy tonight. So stick around if you have questions. And I'll see you Wednesday. Have a good night. Bye-bye.